What we covered in the last slides were the electron geometries. Now we can talk about the molecular geometry, which could be different because while lone pairs take up space, they don't show up in the overall molecular shape. So they're going to affect the molecular geometry, but they're not seen as points in the molecular geometry. It's also important to know that if you don't have the same thing bound in every spot, you can get shifts in your molecular geometry. So for example, in formaldehyde here, you would predict bond angles. Well, we have 3 groups around our carbon, so you're predicting trigonal planar, which is 120 degrees. But in reality, hydrogen takes up less space than oxygen. So the oxygen here pushes the 2 hydrogens together, and we get a little bit wider bond angle between hydrogen, carbon, oxygen, and a little smaller bond angle, hydrogen, carbon, hydrogen. Lone pairs also distort electron geometry, and it might not be in the way you predict. Lone pairs take up more space than predicted. So here in ammonia, it's tetrahedral. You have 3 hydrogens and 1 lone pair. In reality, that lone pair takes up a little bit extra space and pushes the hydrogens together. And so instead of the ideal 109.5 degree angle, we get an angle of 107 degrees. Okay, so linear always has 2 atoms bound. When we get to trigonal planar, if there are 2 atoms and 1 lone pair, we get the molecular geometry of trigonal planar bent. That bent angle is less than 120 degrees because that lone pair takes up extra space. So our example here of sulfur dioxide, the angle here is less than 120 degrees because that lone pair takes up extra space. When there are 4 electron groups and one of them is a lone pair, the result is a pyramidal shape. And so your example there is ammonia that we looked at a couple slides ago, where we have 3 hydrogens bound and then 1 lone pair. And in that case, our angle again was less than the 109.5 degrees that was predicted. And then when there are 4 electron groups and 2 are lone pairs, that's also called a bent shape, but in this case it's tetrahedral bent. The example there is water, and again our angle is less than 109.5 degrees. So here is an ideal geometry. Methane has the 4 hydrogens coming off the carbon with a tetrahedral. Ammonia has the pyramidal shape where our bond angle here is less than 109.5 degrees. And then water is a tetrahedral bent shape. And so the electron geometry is tetrahedral, molecular geometry is bent, and our angle is less than 109.5 degrees. So to predict the shapes around central atoms, first you want to draw the Lewis structure, count the number of electron groups around the central atom. Then you can classify the groups as a bond or a lone pair. And then in your book, there's table 10.1 that's going to determine the shape and the bond angles. So that's going to be the easiest way to do it. And then as you get the hang of it, you'll memorize those shapes and just be able to do it by memory. All right, an example here, predict the bond angles and molecular geometry in sulfur dibromide. So So our sulfur is going to be our central. What we have 2 bromines here, BRs. Draw some bonds. Bromine comes with 7, so 2 times 7 plus 6 from our sulfur gets us a total of 20 electrons. So draw in my lone pairs. And I get this for my Lewis structure. I have 4 electron groups, 2 lone pairs, and 2 bonds. That gets me, the 4 electron groups gets me to tetrahedral. And then the fact that it's 2 lone pairs and 2 bonds makes it bent. So my actual shape is not linear like that. A better way to draw it would be with the bromines kind of down at an angle to indicate that it's not linear. These lone pairs are taking up space up here. Next, predict the molecular geometry and bond angles in silicon pentafluoride. So my silicon is going to be in the middle. I'm going to have 5 fluorines around it. 3, 4, 5 fluorines. My silicon comes with 4 electrons plus 7 times 5 gets me a total of plus 1. Gives me a total of 40 electrons. The 1 comes from the negative sign there. Fill in my lone pairs. Then count my electrons, make sure I'm right. Yep. That gets me my 40 electrons. So I have 5 groups. All are bonds. And so that gets me my trigonal bipyramidal structure, which has 120 degrees for my equatorial and 90 degrees for my axial positions. So there's what that looks like. One more question. We have our phosphorus trichloride here. What is the molecular shape? We have 4 groups, but 1 is a lone pair, so 3 atoms around it gets me, which gets us our trigonal pyramidal shape.